I'll give a minute for people to come up. Hi, everyone. We'll get the colloquium started in a minute. Welcome to all the prospective students. For those of you who don't know, today is one of our 2 prospective graduate student visiting days, so we're really happy to have all of you who are here visiting. So I'm going to go ahead and introduce Tova Holmes. Tova is a professor at the University of Tennessee at Knoxville. She did her undergrad degree at Harvard and then went to Berkeley for a PhD and a postdoc at the University of Chicago. She is a Dewey Early Career Award winner and a Cottrell Scholar. And I've worked with Tova for a number of years on the ALEX experiment. She's an expert in tracking and trigger systems and beyond standard model searches. And she is one of a new generation of people leading the charge for a Muon collider, which is an exciting option for a future collider, and I'll let her tell you more about that.
Thank you, Lauren, for memorizing so many facts about me. I really appreciate it, and thank you all for having me here today. So as Lauren said, I'm going to talk today about muon colliders. And before I get into a kind of wholehearted spiel about how we need a new multi-billion-dollar machine, I wanted to take a second to first try and motivate why we want to study the energy frontier. So let's talk about why that's valuable to begin with. So in some basic sense, we're exploring this frontier for the same reason that we would want to explore any other frontier. So we're trying to explore the unknown, right? And so if I can draw a bit of an analogy, this is sort of much like the exploration of the universe. So we want to know what's out there that we haven't looked at yet. And we're hoping that by looking in new places or by looking in old places with more precision, we can get new fundamental knowledge about how the universe works. And in fact, these 2 efforts, so exploring the energy frontier and exploring the cosmos, or the final frontier, are deeply intertwined on a more fundamental level. So they kind of feed back on one another. So for example, studies of the cosmos told us that there was dark matter out in the world, which set particle physicists on a many decades long search to find out what the nature of that dark matter was by looking at colliders and underground experiments, by pointing magnets at the sun and seeing if you see anything out of that. And meanwhile, just as one small example, particle physicists discovered that particles like neutrinos existed. And then once we knew neutrinos existed, they gave a heating mechanism to the explosion of massive stars, which explained how stellar production could produce many of the heavy elements that make up our world today. So more generally, these 2 frontiers are looking in opposite directions, so to the largest scales and to the smallest scales. But both are trying to uncover the deep mysteries of the universe. So basically, we can look at what we've got now and try to extrapolate backwards by studying the cosmos, or we can study the fundamental particles and try to extrapolate forward by what we know about those particles and their interactions, and hopefully we can meet in the middle. So at the biggest picture level, it's very hard for me to see that. Okay, at the biggest picture level, here's my list of what we're after. So we want to inherently explore the unknown, right? We want to understand the fundamental physics that produce the universe we see today, the particles, all their interactions, as well as the infrastructure of the symmetries that explain them. And we want to understand where we're headed. So what I mean when I say where we're headed is going to be very different from what an astrophysicist might mean. Maybe they mean accelerated expansion of the universe or something like that. But what I mean when I say where we're headed is the Higgs. So if we want to look at this plot, which is kind of small in this room, on the left here, my left, this is showing basically that the measured parameters of the Higgs that we've seen today in our experiments put us in this fascinating, tiny, precarious space where we can't tell if we have a stable universe that will continue to exist like it is today, or if one day the Higgs will tunnel out of its current vacuum state into a new minimum or just roll out to infinity, and that will make all of the masses of all the particles in the world giant all of a sudden, and our entire universe will collapse into itself. So it's interesting to study the Higgs. So I want to go back a little bit with that little teaser of why it might be kind of, the Higgs might matter, the properties of the Higgs might matter. Let me step back for a minute and talk about the Higgs itself. So very famously, in the 1960s, a few people wrote down the Higgs mechanism. So this is essentially this Lagrangian here that you can see. And basically, this Lagrangian is for a scalar field, but because of this minus sign, because of this plus sign in this Lagrangian instead of a minus sign, which you would normally have for a scalar field, you get this super funky shape of the Higgs potential as a function of the field value. And you get this wine bottle shaped potential. And the key feature is that it's minimized at non-zero values. Okay, so the lowest value of the field is not at the center of this potential. This gives us what we call our spontaneous symmetry breaking, when we essentially recenter our Lagrangian at one of these minima. And what it does is, mathematically, it just pops out all of the mass terms that explain the masses of all of our other fundamental particles. It solves all the pesky gauge invariance problems that we had in writing this down in the first place. And it really lets us write down the properties of the standard model. Okay? And so we spent a while, in the 60s we wrote this down, and then 60 years later, we actually observed this particle, which is an incredible feat of prediction. Okay, so we measured the Higgs mass and this vacuum expectation value. So if we we basically measured these two parameters. And if we take this Lagrangian to be the truth, then we're done. We have found all the free parameters. We know the theory. We're set, right? But what we didn't do was observe anything to do with this potential, okay? We have never seen in particle physics that we have a potential that's shaped like this, okay? So as far as we know, it could look like one of these funky shapes that are up here on the top of your right, okay? So we have no proof that they don't look like that. Those are all compatible with the current measurements that we've already made. In fact, our actual Lagrangian could create a potential that looks like anything between these error bars, okay, according to the measurements we've made. So basically, you only know what's at the bottom of this potential well. Everything else is still unknown. And at the high-end tail, that's basically telling us something about the stability of the universe, right? So can we tunnel out and suddenly collapse our universe? Oops. And at the low-end tail, this is telling us something about how electroweak symmetry breaking occurred in the first place, how we went from something centered at zero to something not centered at zero, which in some ways describes the birth of our universe. So captured in these big uncertainty bars on either end of this diagram are the birth and death of the universe. So so we maybe want to explore it, okay? So to really explore this potential, to understand if this really beautiful mathematical structure is actually the truth, the right way of thinking about electroweak symmetry breaking, and maybe even start to understand why a little plus sign is determining the entire existence of our universe, we really need to study this potential in detail. And so as it turns out, to explore out of this potential well, so to get out of the bottom of this thing and actually make measurements there, what we need to do is make multiple Higgses and watch how they interact, basically to expand in powers of Higgs potential out of this potential. Okay. So we're going to do this with the high luminosity LHC, all right? And it will get us part of the way here. So up in the top right here, you can see what happens when we like with what we think we can do with all of the data that the high luminosity LHC can get us. And obviously it looks a lot better, right? But in particular, you'll notice at the bottom end, we haven't done that well. We really won't understand that question of how, what things look like at the actual symmetric point of our field. And so to make a really precise measurement and nail this down, what you need is higher energy. So the bottom right shows if you had a 10 TeV collider, this is what you'd actually be able to measure. So you really be able to see the precise shape of this thing and start to understand if it does look like this. Okay? So of course it's not just the Higgs we care about. As Lauren said, my specialty is in BSM physics. And so coming back for a second to the concept of dark matter, I want to talk about the WIMP miracle. So early on in this many decades now quest to understand what dark matter could be, we came across this sort of coincidence that basically weakly interacting particles with the masses at a few TeV scale could perfectly explain the observed dark matter abundances. Okay? It was a nice little sign that maybe we had hopes of understanding what this could be with the stuff we already knew a little bit about. And if you look at this plot on the right-hand side, this black line, these vertical black lines, represent what that target would look like. How massive would this particle have to be in order to correctly explain the observed dark matter abundances? And then the colored lines are showing for a bunch of different search strategies what center of mass energy would you need in order to detect that target. So you can see for these two, in these particular cases, they're both motivated by supersymmetry, but it's not that important. For these two, our thermal targets are well out of reach of the LHC currently. But if you had this green stuff, the 10 TeV collider, you'd be able to see them in multiple channels. Okay? So it gives us hope for the idea that we could actually see WIMP dark matter, this beautiful, in some sense, simple mechanism for explaining dark matter at the next collider if we could just get to the 10 TeV scale. So basically, I'm giving you a few reasons to motivate the concept that this 10 TeV range is our next major target for exploring the energy frontier, and that we have specific things we want to address at that scale. So right now, we could make fundamentally new measurements of the Higgs, and we could do searches for dark matter, and those are two things we know exist. So those are nice things to have as really concrete targets. So the rest of my talk will be about how we do this. Okay? So when we're thinking about what to do next, it is useful to look back at what we've done so far. So what we've done so far is genuinely the most reasonable thing you could think to do. We have taken advantage of the stable charged particles that the standard model provides. So stable particles are just sitting around. You can, in some sense, gather them up, and then you can use electric and magnetic fields to manipulate them if they're charged. So these make great candidates for wrangling into a beam and using in a collider. So while they're both stable charged particles, the electron and proton, colliding the two of them looks extremely different. So an electron is a fundamental particle. So that means that when you collide an electron and a positron, you're going to have all of the energy of that electron and positron going into the collision. They'll make something, and then that thing maybe will decay, but that's kind of all you'll see, okay? Meanwhile, a proton is a composite particle, right? And so that means a couple of things. One, it means that the energy of the actual collided constituents, meaning the quarks or the gluons that are sitting inside of the proton, are going to determine the actual center of mass energy. So while the LHC is technically running at 13.6 TeV center of mass energy, its actual collisions are much smaller, maybe exploring 1 or 2 TeV. And the other problem is that lots of other stuff is going to come out. So basically, if you imagine colliding 2 bags of trash, then you're just going to have a spray of other things coming out of the bags of trash. It's a really good metaphor. Okay, so you might be thinking, like, this one sounds better, right? So the question is, why would you ever even bother with this one, okay? And there's a very good reason why you might bother with that, and that reason is synchrotron radiation, okay? So synchrotron radiation has this inconvenient property that it scales like 1 over mass to the 4th of the particle that you're trying to accelerate. So this is basically just the concept that if you put a charged particle in a circle, it's constantly radiating energy. So if you're trying to get it to higher and higher energy, it's constantly losing energy, and so you basically just hit a wall where you can't accelerate it anymore. And that wall is highly, highly, highly dependent on the mass of the particle that you're talking about, okay? In fact, if you look at the mass of the electron, which is around half a MeV, or the mass of the proton, which is around a GeV. That difference in masses means that an electron is going to radiate 11.5 trillion times more energy for every pass through a circle that it goes through. So it's an issue, right? So that's a real problem. So what can you do and still take advantage of these nice properties of an electron where they're fundamental particles? Well, you have two options. You can put them in a linear collider, right? So you're still accelerating them. You're not going to have no radiation, but you won't have the synchrotron radiation. You don't keep them constantly in a circle. So that's better, but you're still basically going to have a other severe problem, which is that you don't have a whole bunch of passes to get them up to the energy that you want. You basically get one pass shooting them down the line, and then you're done, right? So it's very hard to get the amount of data you want from one of these systems, and it costs a lot of power to do it because you have to basically every single collision, you have to get all of those electrons up to energy and then throw them away. The other thing you can do is use protons in a circular accelerator. So that's why we do that. And in fact, essentially these two concepts roughly cover the last century's worth of exploration of the energy frontier. So this includes most of the discoveries of the particles of the Standard Model. So this shows essentially the key discoveries of particles since the 1960s and the machines to scale that they were made at, okay? So early on, we had lots of development in this area. The quarks and the tau and the charm were all discovered here. The charm jointly with a tiny proton-proton machine at Brookhaven. And then we start building bigger proton-proton colliders like the SPS. And meanwhile, we also made a smaller ring at low energy that had electron-positrons in them at DAISY in Germany. And we're starting to fill out the Standard Model. And basically what you can see here, which is hard for me to see, I have to crane my neck. All right, what you can see here is that essentially over the last 30 years, all of our discoveries have been in these increasingly large proton-proton rings. So that's basically been our move for quite some time, okay? So we had the SPPS at CERN, then the Tevatron at Fermilab, and finally the LHC, which discovered the Higgs in 2012. So this is how we've known how to explore higher energies. So the question now is, how do we go forward from here? How can we make sure this energy exploration continues? And how can we build towards our next discovery? So what happens if we stick with the current discovery mode of just using proton-proton colliders? So the main constraint here comes from the magnets you need in that collider ring to basically keep bending that beam to stay in its path, right? And the higher momentum beam, the harder it is to curve it so that it stays in the path. And in particular, the scaling relationship looks like this up here. Essentially, you can, if you make your beam more energetic, you have to make it larger to compensate for it, okay? And there's no way to beat this limit. In fact, this limit is a little bit of a lie. It's like what happens if you have your entire ring filled with exactly this magnetic field. So in practice, this is even giving you a lower bound, okay? So if you were going to take our 14-ish TeV LHC collider and you wanted to just go to 100 TeV, which incidentally would get you something like a 10 TeV center of mass collision, you'd need either you keep your magnets exactly as they are and you need to make the ring 7 times the size, and it's already 27 kilometers, so that's kind of a bummer. Or maybe you can build a little bit better magnets, right? So maybe you can double your magnetic field and it only has to be 3.5 times the ring size. Which it turns out that one is almost exactly what the plan is for the proposal for building the next proton-proton collider at CERN. So this is basically saying we'll double our magnet field and we'll have a 90-kilometer ring, which is around 3 times the size of the current LHC. Okay? So the question is, can we do this, right? So that's an unanswered question. I would say to be determined. There's lots of people currently working on understanding the feasibility of this proposal. So maybe you can do this, right? Maybe our next step in the energy frontier could be building a truly giant proton-proton collider. But if you do that, it's a dead end. I don't think anybody believes that you can build the next one after that, right? This is getting to be very, very large. And in particular, I put it over here, just so you guys can get a sense for the actual size. You basically have all of Palo Alto nudged into the little corner of the FCC ring. And this is a 90-kilometer tunnel, right? It's not just that you have to dig a 90-kilometer tunnel. You also have to then fill that 90-kilometer tunnel with the best magnets anyone ever made, okay? 90 kilometers of them. All right, so this is a very challenging, expensive way to go, okay? Maybe possible, maybe the way we'll end up going, but probably you couldn't do the next one. Okay, so another challenge that we have with proton-proton colliders is dealing with the backgrounds, okay? Almost all of the stuff that comes out of a proton-proton collision is very low energy QCD stuff, okay? So we're getting just lots of quarks and gluons popping out, but not doing anything very interesting. Okay, and if you wanted to study the Higgs, say, or study electroweak dark matter, you would have to swim through many, many orders of magnitude of this junk to you in order to find that stuff, okay? Now, at a lepton collider, this is not the case. At a lepton collider, there isn't strong production, so you're basically, most of the time, getting something electroweak out. You don't have to sift through this giant pile of QCD stuff to find anything interesting. So the idea is kind of maybe if we want to study electroweak stuff, it's useful to start with particles that are electroweak charged and not strongly charged, so you don't have to deal with these giant backgrounds. This is kind of a slightly flawed plot, so I wouldn't take the exact numbers too seriously because of the way the total cross-sections are defined, but it's basically saying what fraction of stuff coming out is a Higgs at a muon collider versus a proton-proton collider. And as you can see, the number of orders of magnitude down you have to go at a proton collider is pretty dramatic. Okay, and like I said earlier, in order to study this Higgs potential, it would be very useful to be able to make a lot of Higgses simultaneously, okay? So these two plots show, they're very busy, but I'll walk you through them. They show how often you're going to be producing a certain process based on the center of mass energy of a lepton collider, okay? So the one on the top is showing mostly two bosons, so it could be, you know, your vector bosons, W's and Z's, or those combined with a Higgs. And on the bottom, you're having, it's triboson processes, so you can have two Higgses or even three Higgses in the black on the bottom. The solid lines are basically what happens when you take a muon and an anti-muon and you collide them and you produce these vector bosons directly and the Higgs directly. And the dashed lines are something much weirder, okay? So the dashed lines are what we call VBF processes. That stands for vector boson fusion processes. And it's basically the idea that once you get a muon beam going fast enough, going to very high energy, it effectively gets surrounded almost permanently by a cloud of vector bosons. So there's W's and Z's just flying around with those muons. And you can collide those instead of just colliding the muons themselves. And you can see once you get to high enough energy, these things completely take over, right? And if you really wanted to study many Higgses, right, let's have a look at this black lines on the bottom plots. Okay, you really want to be able to turn on this VBF process because you're never going to see this dark line, right? So being able to go to high energy here really opens up the ability to look at many Higgses at the same time. Now, that VBF process thing I just mentioned, it doesn't matter if it's a muon collider or an electron collider. Both of them could theoretically do that, right? This description of the cross-sections would be exactly the same. But the problem is you get limited by that synchrotron radiation, right? And so if you want to make a circular E plus E minus collider, the sort of state-of-the-art one that we've thought of is the XUCEE, which is using that 90-kilometer ring. And that energy tops out before you even start turning on these new cross-sections. Okay, so that's the first line. And you can do a little better with a linear collider. You could start studying some of these processes. But essentially what happens with a linear collider is because you only get that one pass at acceleration, you essentially just have to make it longer and longer and longer in order to make it higher and higher energy. So by the time you're trying to do like this very ambitious proposal, which was called CLIC, which was trying to get to 3 TeV, that's that long line with all of the yellow that's superimposed on this picture next to the LHC in blue and the FCC in olive green there. And so you can see you're getting to something very, very large, okay? So doing this with E plus E minus colliders is quite challenging. So the challenges, as I've outlined, I will summarize, is that using electrons, you run into this synchrotron radiation problem. It means that you can't use a circular collider to go to high energies. And then the linear collider lengths are going to be proportional to energy, plus they consume a lot of power because you only get that one pass. And we like to, where possible, try to be green. But using protons, you are going to lose a lot of your effective energy compared to the beam energy because they're not fundamental particles. So you're going to get something like 1/10 of the beam energy in your actual collisions. And your electroweak cross-section for some of the stuff we're interested in is so tiny compared to all of the QCD backgrounds that you'll have to dig through. So this is where we are with the particles we're familiar with. And now it's time to talk about the muon. So the muon is essentially a higher mass electron, right? So in that sense, you can see immediately that 1/m⁴ thing is going to be better, right? So it avoids the synchrotron radiation that we have with the electrons, which means you can go back to thinking about doing a high-energy circular lepton collider. It's also a fundamental particle, so that means that we're going to get higher energy reach with a comparable beam to a proton-proton collider. And then there's some other kind of cool bonuses. The one fact that I'll kind of get into explaining why it happens in a minute is the fact that as you go to higher energies, the muon collider luminosity increases instead of decreasing. You actually can get more data out of the same power. So there are a lot of good things about the muon collider. I'm excited to hype it up, but the main problem that you get is that they are not stable, right? Muons decay, and they decay quite quickly, okay? They live for 2/millionths of a second. It's not great, okay? And we have never made a collider out of unstable particles before. So the question probably everyone's wondering is like, how would that even work, right? So I'm going to talk about that for a little while. The global community has essentially been trying to answer this question. So how could we create a multi-TeV collider with muons? And here you can see a kind of simplified sketch of one. So you start with a proton source, right? Because there aren't just muons lying around, you have to make them. You slam it into a target and make pions. Those pions decay to muons. You wrangle up those muons, you force them into beams, accelerate them, and inject them into a collision ring. And that's kind of, all of that stuff is what's pictured here. And just as like a rough look so you can get a sense of scale, it approximately fits on a Fermilab campus, okay? So, I'm gonna take a minute to sort of talk about from just like some simple calculations what we can expect a muon collider to look like. So this will be our spherical Cal muon collider before we get into the nitty-gritty. Okay? So this is what we could do, or what we would expect if accelerator physicists can do everything we hope they can do. All right, so first things first, we have to get our muons, right? So like I said, muons aren't just sitting around. It's not like the LHC where we can take a bottle of hydrogen and just grab all the protons out of there. We have to make them. And that is to say that we are production limited with our muons, right? Our limiting factor for our luminosity is going to be the fact that we don't have enough muons. So because of that fact, we're basically going to, so this is how luminosity looks. By the way, this is an equation for luminosity. It's proportional to n squared, where that n is the number of muons in each bunch that you're colliding. So you up this and you're going to get better physics out, more physics out. But because we're production limited, it makes sense to shove all of those muons into 2 bunches. That's how you're going to maximize this luminosity number, right? The more bunches you split it in, the lower this quantity is going to be. So you're basically just going to stick 2 bunches of muons in your collider, and you're going to circulate them, colliding them until they're depleted, okay? So what happens to those bunches? So our muon lifetime is 2.2 microseconds. Again, a little bit horrifyingly short. But special relativity is here to help us. And so the faster we can get those beams going, the longer these particles are going to live, right? So if we have a beam energy of a TeV, for example, we'll have a Lorentz factor of almost 10,000, which means they'll live 10,000 times as long. Okay? So, excuse me. So what I'm saying is that those beams are going to be constantly decaying, but the higher energy we can go, the less frequently they'll be decaying. If you think about this in terms of the average decay time of the muon, it's basically just multiplying these 2 numbers. And what you get is for a 1 TeV beam, it'll be 21 milliseconds that the average muon takes to decay, which is still a very small number. It'll increase if you go to higher energy, right? This will scale linearly with the energy of the beam. And so if you're thinking about how long it takes for these bunches to be depleted and you have to stick new ones in there, at a, say, half a TeV beam, so a 1 TeV collider, you'd have to do this around 100 times a second. And if you went up by an order of magnitude to a 10 TeV collider, it's more like 10 times a second. Okay, and you can tune that a little bit, of course, to, yeah, you can mess around with those numbers, but it's a rough idea. Okay, so the other thing we can think about, based on the fact that we only have these 2 bunches circulating in the machine, is that we're going to have a time between collisions that's basically just how long does it take some particles going the speed of light to go all the way around our ring, okay? And that means between each collision, you have something like 30 microseconds, which sounds short, but it's actually around 1,000 times more time between collisions of our current LHC. So this is actually a huge help. It makes processing this data a lot more viable because you have all of this time that we're not used to having. So this is a nice, easy part of a muon collider. Okay, so like I said, the average decay time for that muon is going to be around 21 milliseconds times however many TeV the beam is, which means that they're going to stick around longer if you have a higher energy beam, right? And so the average number of crossings that a particular muon will make before it decays, you can just kind of combine those last 2 results I quoted. And it's around 620 times for a 1 TeV beam with a 10-kilometer ring. And it'll increase if you increase that energy. And so that's why the luminosity is going to increase as a function of the energy of the machine. Basically, you're going to be able to keep your muons around longer and collide them more times. So it makes your life a little easier if you have a high energy beam here too. Now, the other thing you have to worry about, the beams are constantly decaying, right? That doesn't just deplete what's in the bunches that you're trying to collide. It also makes a whole bunch of backgrounds for you. Okay, so you have a bunch of these beam decays just hitting your detector all the time. And in particular, if you ask what fraction of them are going to decay within 20 meters of the interaction point, it's a very small fraction, 6.4 times 10 to the minus 6 for a 1 TeV beam. But if your bunches have like 10 to the 12 muons, it's a large number. So you'd expect for bunch sizes like that, you'd expect around 10 to the 7 decays in that area. And that is inversely proportional to the energy of the beam, right? If you have a higher energy beam, it takes longer for them to decay, you have fewer decays that are going to happen. If you wanted to ask what's the total energy of all those particles that are going to be decaying and depositing their energy in the detector, it turns out to be a very large number, 13 eV, which is not even a unit you see very often. It's a bunch. But importantly, now the factor of energy has fallen away, right? We've kind of canceled it out. So what this means is that the amount of energy you get from these beam backgrounds doesn't change when you go to higher energies. It's basically fixed. So if you made a really low energy muon collider, you'd have to deal with all of these giant amounts of energy that are getting dumped from the beam-induced background, just like you would at a higher energy muon collider. Okay? So from all of our little math exercises with special relativity there, I want to just point out a couple of key takeaways. So the key E plus E minus collider challenges are going to get harder with energy. So the synchrotron radiation is going to get more challenging if you have a circular collider, and the power and size constraints on a linear collider are going to get harder. The key proton-proton collider challenges are going to get harder. Basically, you need a larger and larger ring for these higher and higher energy beams. But the key challenges for a muon collider, basically keeping your luminosity high and dealing with these beam decays, are both getting easier with increased energy. So as you start going to really high energies, you can see how these muon colliders are getting a substantial advantage. Okay? So I have a couple of other, while I'm selling it, I have a couple of other selling points. So these muon colliders, one, are going to be really compact, right? So much smaller even than the current LHC for a 10 TeV machine. And that means lower cost and lower carbon footprint because you don't have to dig out that whole thing. You don't have to fill it with magnets that you have to power. You don't need as much concrete, et cetera. They're small enough to potentially fit at the Fermilab site, which means that they could be run potentially in the US and even potentially complementary to a CERN program instead of having to wait until a CERN program is over. And because the actual facility size is smaller, you have a lot more of the total cost that's going into new technology, which makes it a little bit easier, one, to sell to, say, like the government, and two, to get partners to contribute to, right? So instead of helping you dig a tunnel, they can help you build a magnet or make something cool. So it's easier to have international buy-in, perhaps. And then, of course, finally, and perhaps most interesting to me, is that it provides a potential path beyond the 10 TeV scale, because none of these scaling relationships I told you run into a problem at this 10 TeV scale. You can keep going with them and then make the next machine. Okay, so I hope by now it's clear that there's a whole lot of potential here for the energy frontier, right? And the question, of course, is can we actually do it? So this is a blown up, so we had our little simple scheme, and here's a slightly less simple scheme for what making a muon collider would look like, okay? So first of all, to start with, you need this megawatt scale proton driver with highly compressed proton bunches to get you started. It needs a target that can handle all of that power without crumbling into little pieces, plus a really powerful large aperture solenoid that can capture all of the muons that come from the pion decays. And then you need to cool the beam by 6 orders of magnitude in order to get it into something that you can actually put into an accelerator. You need extremely rapid acceleration to get to collision energies, and you need very fine-tuned control in the collider ring to optimize the luminosity and minimize neutrino radiation. So just to kind of drive this home, this is what it looks like as you accelerate your muon beam. So this is basically taking an example of an accelerator that ramps from 0 to 7 Tesla in 0.04 seconds. And this is the consequence for how much of the beam you lose as a function of time. So you can basically see that you're rapidly decaying away your beam while it's still at lower energies. And then by the time you get it to a high enough energy, that decay really slows down. So you need to do all of these steps super, super fast, or you won't be able to take advantage of special relativity and have any beam left over by the time you're trying to collide it. Okay. Meanwhile, so that's kind of like a really brief rundown of the challenges on the accelerator side. And meanwhile, on the detector side, which is a little closer to home for me, you have a whole new challenge, which is this beam-induced background, where you're getting all these particles from the beam decays. So the first thing that you do, so basically, just imagine every muon that's coming down from the side of the detector, which is like these, I don't know, these things coming out either way. That's where the beam enters that detector. Every muon that's coming down there has some probability to decay into electron and some neutrinos, okay? And if that is, say, a 5 TeV beam, those are like TeV electrons plus, right? And so it's a lot of energy, right? We saw that EeV number. It's a lot. So what happens is you want to shield your detector from these super high energy decays. And so what the idea was that was used in the early stages of this is to take some tungsten nozzles and essentially insert them into the sides of your detector so that you have all this really dense material that's going to stop these electrons from hitting your detector so that you don't just have them flowing through all the time. And this picture on the bottom shows an example of a single muon decay and what happens because of that. So you can see you get these giant showers of particles that result from each one of these muon decays. Okay, but we expect 10 to the 7 of these within 20 meters of this detector. Not necessarily all of them will hit the nozzle or hit the detector, but a lot more than one, right? So we expect a ton of those. And so just to give you a picture of what this actually looks like from a detector place, so all the way in the very center, so this is a possibly weirder and harder to understand picture of a muon collider detector. So these are our tungsten nozzles, these dark things, and right in between the two of them is our interaction point where our muon-muon collisions will happen. And right close to those, we want to make really high precision measurements of our particles, and we have something called a vertex detector there. And so in that vertex detector, the plot that's on your right is showing what we see. So all of the colored part, right, this color scale, this is the beam-induced background hits in that vertex detector. Okay, and you can look at the scale to see that in each of these bins there's like 750 or something. And meanwhile, these little blue dots that hopefully you can see that are mostly centered over here, those are our signal hits. Okay, so there's like 15 of them. Okay, 600,000 beam-induced background hits in this detector. You have to pull out the 15 interesting signal hits. Okay, so this is quite a challenge from a detector perspective as well. And in general, you have to deal with this beam-induced background throughout your detector. Okay, in your tracker, so that's what we were just looking at. You need a 4-dimensional tracker, which is to say you need to be able to measure where in space and in time each of those hits are to effectively disentangle them from the backgrounds. It would also be helpful to be able to tell what direction stuff came from so that you could also maybe separate things that came from the interaction point versus stuff coming out of those nozzles. In the calorimeter, which is outside of the tracker, you need super high granularity and maybe precision timing there as well so that you can once again disentangle your interaction, your signal interaction from all of that background. You need, in your muon system, which is the final piece, it's not so bad because mostly everything gets absorbed before it gets there, but when you get really close to those nozzles, you have to deal with really high rate decays into your muon system. And then the entire thing, that whole thing has to be fairly radiation hard to deal with all of these decays again. You need electronics on chip in order to differentiate all of these 600,000 hits from the 15 interesting ones before you have to read all of them out of the detector because you can't send all of that data off the detector. And if you do that, you can maybe dodge having a trigger system, which is fun for people who've worked on a trigger for much of their lives. And you also have to figure out how in the midst of all of this beam-induced background, you can maybe make some measurements in the forward region, so close to the beam, so that you can tell what's decayed in that region and measure the luminosity of your detector. So you have a lot of challenges throughout this entire system. So no matter what your particle physics detector expertise is, there's something interesting for you to think about on a muon collider, I would say. And then another interesting challenge here is that everything is completely interconnected, right? So if an accelerator physicist takes their lattice design and tweaks some of the parameters, or changes around the machine detector interface, so like all of the stuff that's kind of controlling the details of how the focus happens, or maybe those nozzles, it completely changes your detector requirements and your physics performance, okay? So this is an opportunity, essentially, to really interconnect those fields of accelerator, experiment, and theory together. And a cool thing is that this is really already happening. So compared to anything else I've ever worked on in my career, this is like the only place where I've had all of those three groups actively working together fairly continuously. And so, it sounds like quite a challenge, but I can show you that we're already making progress on it. So on the left here is a plot that my group made, which is utterly incomprehensible without having somebody spend quite a while explaining to you what the details are. But essentially it's just a ROC curve, so it's just showing you how much background, beam-induced background rejection you can get and how much signal you can keep. And we're varying multiple parameters that you could maybe cut on, so that's why you get planes instead of lines. But anyway, the point is you can see that you can get like order of magnitude reduction in your backgrounds without having any real issues in your signal, which is great. Meanwhile, so this is all for the tracker. On the calorimetry side, we've developed some algorithms for doing some beam-induced background subtraction so that you can still sum up all of the energy that gets deposited in that calorimeter and make a pretty good high-resolution estimate, the smiley face one, of what your energy was. Meanwhile, we've been spending a lot of time trying to increase the realism of our detector design and our simulation and reconstruction so that we can say that we're not just doing a simplified version of this, we're really starting to explore the limitations of these detectors. So, for example, we, in expanding for the 10 TeV detector, we had started with a 3 TeV detector. We needed to make everything a little bit bigger, which means we had to reorder where the magnet in the system was, because you can't just make an infinitely large solenoid. That turns out to be hard. That's a fact I learned in this. And essentially, if you stick your solenoid before some other pieces that are going to measure it, it blocks a bunch of the radiation, which is great, but it also totally messes up all of your reconstruction software. So there's some interesting low-hanging fruit here of like, okay, we redesigned our detector, now we need to be able to know when electrons are coming out. And so these plots on the right show some plots that I made while we were trying to fix a bunch of problems that we created when we re-optimized our detector, where the blue line is essentially showing how good we were at finding electrons, and it was like at embarrassing %. And we're slowly kind of finding the problems that we created and fixing it back up. So now the bottom one is showing that our tracks are working really well, but we're still having trouble associating those with stuff in the calorimeter. So we have lots of things to do where we can fiddle with this, but we have to then keep trying to figure out how to actually get physics out in the end. And actually getting physics out, we've been able to do some really nice full simulation that show that we can get some physics out. This is a very old plot. This was made in like, I think 2021, something like that. That was somebody trying to say, look, we can disentangle a Higgs from a Z-boson at a muon collider. So the Higgs peak is the red one and the green one is the Z peak. And like the data is the black dots, right? And so someone was like, yeah, look, we can see both of these curves. We were able to fit both of them and tell there were two there. And I think everybody agrees, if you look at that, it kind of looks like you can't separate the two curves, right? So I find this one very embarrassing. It's several years old now. But that exact thing I showed you where we got so much better energy resolution in our calorimeter, we're propagating to this study, and I think very soon we'll have a much more convincing version of this plot that shows that we really can disentangle these two. Meanwhile, we're even able to do some interesting stuff in unconventional signatures, which is like a separate passion of mine. So basically, what happens if you have not just really simple standard model particles coming from your interaction point, can you reconstruct that too? And in particular, this is a disappearing track search, which is actually one of the key signatures you want for that WIMP dark matter thing that I mentioned at the beginning. And somebody was able to show that we were able to very nicely reconstruct those even in the presence of this beam-induced background. So overall, I think this is a really exciting project. It has an interesting history. So this is a plot that I made by scraping the archive data. And it's basically showing you how many talks or how many papers there are on archive about muon colliders as a function of time, and the colors show which field they're coming from, okay? And so you can see in it the history of muon colliders, at least in the last couple of decades. In the 90s, or in the early 90s and early 2000s, there was a proposal for a muon collider plus neutrino factory program. and there was some interest there. It didn't really get off the ground, I would say. There was a lot of theorists who were interested in it, not as many accelerator people, no real experiments interested. Well, anyway, not a lot of experiments interested. In the sense that nobody was talking about actually building anything on the detector side for this, right? That's the blue. And then in 2013, or in the early 2010s, there was the MAP program, which was an accelerator, Muon accelerator program. They were looking to build a Muon collider Higgs factory. So a pretty low energy by my standards Muon collider. And as you can imagine, the fact that it was low energy and that you could do it, you can reach those energies in other ways, made it not a very compelling program to any theorists. So there's like no, theorists can easily write papers, right? So you should downweight the purple. But they didn't even write papers for this thing, right? There were no real theorists engaging in this time because, you know, people were seeing, oh, there's all this beam-induced background, we can do it with the electrons and positrons, why would we do this, right? So that program made a lot of interesting advances on the accelerator side, but it didn't have the real engagement from the whole community because the physics case didn't totally make sense with where we were at the time. And then finally, you can see in the lead up to this most recent snowmass, this is when you actually get all of the different areas engaging at the same time. So this is experimentalists, including instrumental theorists and accelerator folks, all engaging in the snowmass process, and like I said, actually working together. So I think it's very hopeful that we've actually gotten to the state where we found something where it has a really good physics case, the accelerator stuff is starting to mature, where people on the accelerator side are very engaged. It seems like the time is right for a Muon collider. And so we've done a lot of community building. This is one picture at Fermilab of a Muon collider workshop on the top, and one in Orsay in Paris of the International Muon Collider Collaboration. And put in a lot of work to the various sort of like snowmass process and the equivalent in Europe. And we got a ringing endorsement, I would say, out of the P5 report, which recently came out, and even went so far as to make a terrible pun and say this was our Muon shot. And basically it was a report that set up a Muon collider as plan A for Fermilab. So there's quite a lot of work still towards making this a reality, and this is a little bit more detailed image of what a Muon collider at Fermilab might look like, because it's really stretching the bounds of what you can fit on that site. There's quite a lot to do, plenty of challenges that still have to be overcome, but it seems like the time is really coming together now, where we can start to think about making this our next step in our exploration of the energy frontier, and maybe even do it in the United States. So, thank you.
Thank you, Tova. Questions? Okay.
Thanks for the talk. Do you think this technology, I guess, that artificially accelerated produce those muons could be used to replace the cosmic ray muons we use to image large-scale objects? They're like it could be monochromatic, they could be high energetic, so you could find a way like to cool them.
Yeah, people have definitely played with that. I will say, like, that's a very long way off, right? So it's not like we're not anywhere close to being able to think about how to make a portable muon beam, right? But people have sort of like, you know, sort of mentioned that as a far future application. I would say it's quite a challenge. Like for now, you know, we really need a huge, like making a proton source is pretty challenging and site-specific thing to start with, and then you have to sort of make the rest of the infrastructure for the well, you don't necessarily need to do cooling for that. But anyway, I think it would be challenging. People kind of, I've heard people suggest it, but I don't think it's a near future thing. Some people have suggested that, I didn't talk in detail about the neutrinos that come off of this beam, but some people are interested in doing physics with the neutrino beams that come off of it. And I've had several people ask me if you could point it at Ice Cube. So there's some interest in that. The answer is it's kind of hard to do that. It's hard to point things down that much. But yeah, no, it's a good question. People have brought it up, but I think it's not a near future possibility.
Two quickies. What's the timescale for building this machine? And is there any interest in muon proton collisions?
Great. Okay, so to answer your first question, it's a little hard to assess exactly what the timescale would be while we're still in the kind of proving that the challenges exist phase. But there, in the SNOMAS process, there was the kind of independent task force of accelerator experts that tried to come up with timelines for all of these things. And for the future colliders, they tried to do a technically limited timescale. So if we got all of the money in the world, how long would it take? And their number for a muon collider was 2045. Your second question was about muon proton. Yes, there's a proposal to do what's called the MUIC. So it's basically the EIC, the electron ion collider, with muons instead. So could be protons, but probably you would also do other ions. They have an interesting proposal. You basically can access a different phase space than what you can do with the EIC. There's a little bit of trickiness in terms of where you would site something like that, right? So that would have a more natural location at Brookhaven, and then would you want to then build a whole muon collider at Brookhaven? Maybe that's like an interesting staging option. So there's some tricky parts around it, but yes, there's definitely people actively interested in that and working on it.
Let's see, this one and then that one.
Oh,
Yeah, go.
me?
Yes.
Okay. Thank you for the talk. Very, very interesting. There's one graph that you showed where you show basically that you lose quite a lot of particles early on.
Yeah.
I suppose because they're just not very fast in the beginning.
Yes, exactly.
Is there the assumption there, and I'm wondering with future technology or now upcoming technology that improves the accelerating fields, if you can leverage that to, well, not throw away 80% of your charge at the beginning.
Yeah, so the faster you can do this, the more of your muons you can keep, right? So this one is made, the specs that went into this plot I made are using some kind of a set of specs that some of the INCC folks made for what they thought might be feasible. But there's a lot of error bars on that. So if you can do a little better with faster acceleration in the early stages, you can really up your luminosity. So yeah, I think it's definitely, let me put it this way. There's a whole bunch of things that we're working on where we're like, okay, maybe we can get this to be this value within a factor or two of so, right? And so, you know, maybe one of them is going to go down by a factor of 2 and another one will go up by a factor of 2, and we hope they'll average out or something like this. We hope that they don't all go down by a factor of 2 so that we lose luminosity. So yeah, maybe if we have a little bit lower performance in some other area, we could compensate with better fast acceleration or vice versa. Yeah, definitely a limiting factor.
It seems such a shame about the beam-induced backgrounds. Those electrons are pretty boosted.
Yeah.
They have some rigidity, and their energy is comparable to the muons in some sense.
Mm-hmm.
Possibly close to Higgs production scale. Maybe this is sort of my question. Why not? Are people coming up with ideas to essentially make fixed target, like really rearrange the detector to use the electrons as a fixed target source for physics?
Yeah. So let me first describe what will happen to those electrons, right? So they'll have a kind of range of energies that are below the beam energy, right? Which means that the magnets that are curving the beam will curve them all inwards, right? So you'll get a whole bunch of electrons that go in towards the machine, and it's basically a spectrometer then, right? Like you're going to get different amounts of curvature based on their momentum, and they're sort of continuously decaying as they go around. So what you're going to get from that is kind of a continuous spray of not monogenic energy electrons. It's pretty hard to, you're not going to have, so what you can have, again, I didn't get into this at all, very close to your detector, you tend to have a straight section in your accelerator, right? Because you want to do all that focusing and stuff. You don't want to put dipole magnets in the middle of that are curving the beam. So you have a straight section there. Some of your electrons will come right through that straight section, but they're still always going to get curved inside. Like when they come out, they'll get curved inwards. Your neutrinos, meanwhile, will be unaffected by the magnetic field, so they'll go straight down the line of that straight section. So it's very easy to put a neutrino facility at the end of that straight section, and I think that's definitely very interesting. But it's very hard to wrangle the electrons into a useful place because of the fact that it's sort of going to be continuous no matter what you do. So there are some ideas about, yeah, like maybe, you know, you have beam dump experiments. This would be a very high rate of electrons with very high energy, so you could just choose a place to instrument and do something cool with them. But you won't have nearly as high the intensity as you can get from the neutrinos. So there's some folks thinking about that. There's also a lot of ideas about how you could do a beam dump experiment in basically the ramp up to building a muon collider. So let's say you can make like one beam at a lower energy. You're doing some demonstration of your cooling, for example. Can you stick something at the end of that where you can actually do physics along the way? So most folks' attention have been on that question more. I think having more people think about the question that you asked would be very welcome.
Thanks.
What is the plan for demonstrating more cooling?
Great question. So there are currently several proposals. Most of them, the explicit proposals currently are in Europe. So there's 2 proposals in Italy, one at CERN and one in France to set up a cooling demonstrator. Some of those are a little more complete than others. But the idea is that you want to actually have a serious proton driver, so it's nice to put it maybe at CERN and use some kind of like beam dump facilities. And you want to be able to show multiple cells, not just, so right now the only proof of principle has been with a single cell. So people are trying to figure out how we could get significant intensity on the beam and show a few of them in sequence. And there's 2 sites that have been picked out at CERN that you can potentially do that at. So those are, I would say, there's an INFN one that's a fairly reasonable one that I don't know all the details of the upstream driver for. But there's a couple of proposals that are really looking at how to do exactly that. And the goal is to try and build one of those, or start building one of those at around a 5-year time scale.
Just a quick follow on that. So how many orders of magnitude on cooling do we have to go from what's been demonstrated in the last round?
Well, it's a little bit hard to put a number on that because it was one cell that was demonstrated, but if you took the numbers, if you just took the numbers from what was demonstrated and the simulation that extrapolated that, then we're basically at what we need. But the problem is that those don't include like multi-muon interactions, and there wasn't a high intensity muon beam that the single cell cooling was shown with. So there's an open question of how much worse does it get from those muon-muon interactions. So I would say the exact number on that is it's uncertainty. But you know, maybe an order of magnitude. Yeah.
How good the mitigation needs to be so that it doesn't ruin the physics inside?
That's a good question. It's different for every detector, right? So let's say in the vertex detector, it looks like, we've been looking at, you need 25 by 25 micron pixels, and you need to have a timing resolution on each of those I would say you could do something, basically then the constraint is, okay, how bad do you want your readout problem to be, right? So the better the timing precision, the less readout you have to do, and therefore the less materials you have to stick in your detector to deal with the cooling for that and the cabling for that and all of that. So there's not a hard number, it's an optimization problem, but if you can get maybe hundreds of picosecond timing, then you can probably do okay, and if you can do better than that, then you can do great. And in the calorimeter, this is really, really dependent on your precise detector design. So if you can make it so that your solenoid is inside of your calorimeter, and so basically the solenoid can actually absorb a fair amount of the beam-induced background without quenching, then it's actually not very bad at all. You can do something kind of like the CMS upgrade calorimeter to make that work. So I would say a lot of the detector problems, which looked very scary when people first started looking at this, now that we're sort of, let's say, facing down the high luminosity LHC detector challenges, we're thinking, okay, these are only a step away from what we're already working on. So it's looking much more feasible, I would say. Go ahead.
And for the slides 41, you showing the signal or background rejection thing.
Yes.
So far, is it just cutting on the timing and angle there?
Yes, yeah, there's a, so this is, I can show an actual drawing of what this is. If you're curious, this is these variables. So these are basically, let's see, on the top right is if you, so all of the rainbow stuff is your beam-induced background and the red stuff is signal. And the x-axis is the time that you measure for a particular hit in the vertex detector, and the y-axis is how much that time differs from what you would expect for a particle traveling the speed of light to wherever the point on that detector is from the interaction point. And so you can see you have quite a lot of structure in this space that you could cut on. You can basically remove a big chunk of this beam-induced background if you're able to get sub-nanosecond resolution. Okay, and this plot here is showing a similar concept for the angular distribution. So this one is already subtracting off the difference from expected angular distribution based on where in the detector that hit is, and it shows how that varies as a function of z, so going along the beam pipe. And you can see again that there's these big interesting shapes in the beam-induced background that if you could get decent angular resolution, you could cut away all of that beam-induced background. This is kind of a generic thing that's just not making any specific requirements on what your detector would be to get that angular measurement. But this one is just showing a study of how once you get small enough feature size, you can actually use the cluster shapes on their own to get some pretty good pointing information of like where that hit was coming from in your detector. So yeah, that's what's going into those plots.
Any other questions for Tova? All right, no, thank you very much.